All right, guys, section 8.1 is a really long section, so we're going to cut this one up into, I think, 3 different videos, and we'll do them one at a time right now. So moving on into chapter 8, we're getting away from the concept we did in 7 of similar triangles and similar polygons, and we're going to start talking specifically about right triangles. And right triangles, as you probably recall, are triangles that just have one right angle and then 2 acute angles. And the first thing we discuss within this chapter on right triangles is the Pythagorean theorem, which is one that I know you guys have learned about in the last couple of years in other levels of math, but we hit it pretty hard here in geometry. But as a little bit of a precursor skill here, before we get into the Pythagorean theorem, we're going to talk about this concept right here of simplifying radicals. Now, before we get too far into it, though, I do want to point out, for those of you who have your own calculator, if you bought one of the newer Texas Instruments ones, specifically the TI-30 XS Multiview that we recommended that you guys buy, that calculator is going to do most of this work for you. But if you don't have one of those, or if you're using a phone calculator or some other one that you found online, this is something you're going to have to know how to do by hand. So let's start talking about radicals. And when we discuss radicals, we normally mean at this level what you guys probably call a square root sign. Now, we don't generically call it a square root sign because next year in Algebra 2, you guys are going to start learning about something called cube roots, which would look maybe something like that. We're not going to have any of those this year. So when we see that symbol this year in geometry, we're just going to call it a square root sign or a radical. And when we ask you, like here in example A, what the square root of 49 is, the question simply is what number multiplied by itself is equal to that 49. This number right here is what we call the radicand. So the number multiplied by itself that equals 49, you've probably figured out already in your head, is 7. Now that's an answer you could get by typing into your calculator the square root of 49, and it would tell you the answer is 7, but that's one you should be able to do on your own. Let's talk about example B. When you take the square root of a fraction, there's a little property of radicals that says that the square root of a fraction can be broken down into the square root of its numerator, the square root of 25, over the square root of its denominator, which is the square root of 36. Basically, you can just take the square root of the numerator and the square root of the denominator separately, and that'll get you the square root of the fraction. So the square root of 25 is 5, because 5 squared is 25, and the square root of 36 is 6. So 5/6 is the square root of 25 over 36. Now that middle step right there might be one that you guys can skip as you get a little bit more comfortable with this. All right, so let's talk about example C now, and the plot thickens here just a little bit because we've introduced a variable. This was really just kind of to get you thinking about radicals and square roots, everybody. We're not really going to do anything in here this year in geometry with the square roots of variables, but you're going to see a lot of this next year in Algebra 2. Okay, so we can kind of break this up, and again, kind of using the same trick that I used right up here in example B, we can split up the square root of 144x to the 6th into the square root of 144 multiplied by the square root of x to the 6th, and then take each square root individually. The square root of 144 is 12, because 12 times 12 is equal to 144. And when it comes to the square root of x to the 6th, let's do this off to the side right here. What we really want to know is what number multiplied by itself, the same number in both spots, is going to get us then x to the 6th. All right, and if we remember our rules for multiplying with monomials, what you're going to do is you're going to add these two exponents, whatever they are right here, and try to end up then with an x to the 6th. Well, since it's a square root and they have to be the same, you're just asking yourself what number plus itself is going to equal 6. So we're really just cutting that 6 in half and getting a 3 in each spot. So back to this example right here, the square root of 144 is 12. The square root of x to the 6th is found just by taking the exponent and cutting it in half, so that's an x cubed. And that's our answer there for C. 12x cubed is the square root of 144 x to the 6th. Now D really works the same way as C. We just kind of took it up a level by introducing a second variable. But again, we'll just break this up, and this one I think we can do mentally. The coefficient here of 225, so you're asking yourself, what number times itself equals 225? The answer to that is 15. For the square root of a to the 10th, again, we have an even exponent right here, so you're going to keep the same base of a and cut that even exponent in half to make it a to the 5th. And then for b to the 16th, the base stays the same, and we take half of that exponent and get an 8 up there. So 15, a to the 5th, b to the 8th, that's the square root of 225, a to the 10th, b to the 16th. Now, none of those were super difficult because in every one of those cases, the radicand that was presented to us, like 49, 36, 144, those were all perfect squares. And let me go back to this now. When you take the square root of a perfect square, your answer always ends up being something that looks nice, like 7 or 5, 6 or 12x cubed or 15a to the 5th, b to the 8th. But things get tougher when you're asked to take the square root of something that is not a perfect square, like 50. Now, even if you have a pretty good understanding of perfect squares or square roots, you might have a little trouble with this one right here. Let's go back to the first problem that we did. The square root of 49 was equal to 7. Most people are able to understand that because in their head, they ask themselves, what number times itself is equal to 49. And mentally, they can find that answer without having to think real hard. But when you ask the question, what number times itself equals 50, there isn't any number that you learned as maybe a third or fourth grader learning your multiplication facts. There isn't any number times itself that equals 50. Now, what I just said there is not entirely correct. There's no integer, there's no whole number times itself that equals 50, but there is a number times itself that equals 50. It just ends up being what we call an irrational number, and that's what we're going to try to find now. So the way we go about simplifying radicals, first of all, we have to take stock of the group of numbers out there that are called, right up here, perfect squares. Now there's an infinite number of them, so we're not going to list all of them. But the first perfect square, even though this is one that doesn't really help us at all, is 0. And the reason that 0 is a perfect square is because the square root of 0 is an integer. The square root of 0 is 0. The next perfect square is 1 because the square root of 1 is 1, and 1's an integer. The next perfect square is 4 because the square root of 4 is 2. All right, hopefully you're starting to see the pattern. The next perfect square now is 9 because the square root of 9 is 3. Now, as we're going through the rest of this list, it's probably more helpful to think about it in the other direction. I'm not going to write all of these out, but 0 squared equals 0. 1 squared equals 1. 2 squared equals 4, 3 squared equals 9. So it's probably easier now to start here and then come up with this number. So the next one in our little list right here, 4 squared would be, yep, there we go, 16. That's our next perfect square. 5 squared is 25. 6 squared is 36. 7 squared, 49. 8 times 8 is 64. 9 times 9, 81, and we'll go into the 3-digit squares over here on the right. 10 times 10 is 100. 11 times 11 is 121. 12 times 12, 144, and we're going to go just a little bit further. 13 times 13 is 169. 14 times 14 is 196, and 15 times itself is 225. Now, there certainly are more perfect squares than those. That's just the first, 16 of them there. But those really are as many as we would need for our purposes here. So as to not confuse us moving forward, I'm going to get rid of the work that we did over here to show that. And this is a list here of the first 16 perfect squares. All right, so with those in mind, now we're ready to move over here into example E and try to see what we can do with the square root of 50 to simplify that radical. So the first thing we do is we're going to try to break down the 50 into the product of two numbers. And one of those numbers has to be a perfect square that comes from this list over here. Now we want to think about the biggest possible number we can find that goes evenly into 50. And I'm hoping this was a pretty easy one here. 25 is the largest perfect square right here that we got out of that list that goes in evenly to 50. So we break the 50 down into 25 times 2. Now, the next thing we do is we take advantage of a property of radicals that says the square root of a product is equal to the product of the two individual square roots. So instead of one big square root over 25 times 2, I can now split that expression up into two different square roots. The square root of 25 times the square root of 2. Now, since 25 is a perfect square, we can go ahead and evaluate this. The square root of 25 is 5. 2, however, is not a perfect square. So there's not anything that we can do to simplify that. So the square root of 2 just comes along for the ride. And this, everybody, is in what we call simple radical form, SRF. 5 root 2 is the answer to E. That's what the square root of 50 is equal to. All right. A quick little explanation of that is if you take the number that we came up with, 5 root 2, you would need parentheses here. If you square that, let's take a look at what that does for us. Squaring something means to take a number, 5 root 2, and multiply it by itself, 5 root 2. Well, let's see what happens here. The coefficients, 5 times 5 is going to give us 25. The square root of 2 times the square root of 2 is going to get you the square root of 4. So this is really 25 times, and the square root of 4 is 2, and sure enough, that ends up with 50. That was our original radicand back here in example E, and that's kind of a way of proving what we've got here. So 5 root 2 is the number that multiplied by itself will equal 50. So there wasn't an integer that did that, but there is an irrational number that will do it. Okay, let's take a look at F here. This problem seems easier than the one we just did because 24 is a smaller number, but there's a reason I wanted to go through it. Actually, this one isn't as bad as I thought. So we're going to try to split up 24. Let's go back over here to our list of perfect squares and try to find a perfect square that divides evenly into 24. Obviously, starting right here, 25 is too big. 16 doesn't work, 9 doesn't work, but 4 does. So the square root of 24 becomes the square root of 4 times, and that's going to be a 6 there. We're now going to split this up into the square root of 4 multiplied by the square root of 6. And the square root of 4 we can evaluate to be 2. Not the square root of 2, just 2 by itself. You can't do anything else with the square root of 6, so that just tags along, and the square root of 24 simplifies now into 2 times the square root of 6, or 2 root 6 is kind of the fast way to say it. Okay, so that was example F. I lost a G here somewhere. Did I miss it? Ah, there we go. This is an interesting one here. G, the square root of 72. Now again, looking at your list, 72 is obviously not a perfect square, so we're going to try to figure out a perfect square that divides evenly into it. And this one is interesting because 72 is actually a cool number that has lots of factors to it. As I go through this list and I think about it, a lot of people realize that 4 divides evenly into 72. A lot of people realize that 9 divides evenly into 72. Both of those are right, but what you'd really like to do is think about the biggest possible number that works. And as a hint, guys, for trying to find that biggest number, here's what you should do. Think to yourself here, what is half of this number right here? Well, half of 72 is 36. That is where you should start looking in your chart, and sure enough, 36 is a perfect square. You wouldn't want to bother checking 49 or 64 or 81 or anything like that because those numbers are going to be too big and are not going to work. So the 72 breaks down into the product of 36 times 2. All right, again, the biggest bite you can take out, there you go. We split this now into the square root of 36 times the square root of 2, and this square root of 36 becomes 6. And the root 2 just tags along for the ride. So the square root of 72 simplifies into 6 root 2. And that was G, and here we go somewhere. H. One other benefit to this, this really doesn't come into play that much if you guys are using a calculator, but let me show you something kind of cool about 576 as we try to split this up. So 576 was too big to show up in our little list over here, so let's start looking for numbers that divide evenly into it. And I'm grabbing my calculator now and I'm playing around. I told you guys to take your number and cut it in half. 576 divided by 2 is 288. That's not in our list and it's not a perfect square. But if I check some of these bigger numbers, I am pretty sure that if we take 576 and divide it by 144, this number right here, we end up with an integer of 4. So that tells us that the 576 can be broken down into 144 times 4. Now, using the trick that we've been doing, we split this radical now, and we make it the square root of 144 times the square root of 4. We evaluate what we can, anything that we can. The square root of 144 is 12 because 144 is a perfect square. I usually like to circle my radicands that are perfect squares. But what's interesting about this problem, for the first time, we can actually evaluate this second factor. 4 is also a perfect square. So the square root of 4 is 2. And we now multiply the 12 and the 2 together to get a final answer of 24. So this is the first problem we've done out of this whole list where the answer has not involved a radical. That tells us something that we probably didn't know. 576, since its square root is an integer, 576 is a perfect square. It's not necessarily the next one in this list, but 576 would go down here in this list somewhere. And if you hadn't thought to check it, if you were to just type in the square root of 576 into your calculator, even a simple one like your phone calculator, yep, we get 24 for the answer there. So being able to simplify radicals is another useful tool for being able to evaluate a square root if you didn't recognize that number as a perfect square. And I had one more to do with you guys here, but you know what? This one involves variables, so I think we're going to skip this example for now. Okay, that's a wrap on what I want to do on the first part of 8.1. I'm going to end this video, and then we'll come back and pick up the actual Pythagorean theorem in the next one.